Hello, I'm Wan, and I'm glad to present our work Understanding DevOps Security of the Google Workspace apps. Google Workspace, Zoom, and Slack currently, they already attracts over 2 billion monthly active users, and we use its native applications like the Google Doc, Google Slide, or Gmail every day. Besides the native applications, they also support over 6,000 third-party applications or named as add-ons. Utilizing these add-ons, the user can edit mathematical equations, insert free images into their slide, or even synthesize their email attachment. This is one demonstration. We can see that there is one attachment in this Gmail, and after we open up this box add-ons, it will automatically scan the corresponding attachment. And after user further click the Save Attachment button, this will be sent to their box account. They can finish this without leaving current interactive Gmail. And there are 3 parties involved in this workspace. The user can utilize these functions provided by the add-ons, and the add-ons, in order to facilitate the user's function, they must be able to access the resources of the user stored on the workspace, and this requires the API provided by the workspace. This is the technical demonstration of the running process. The user will interact with the add-on through their browser, and after user has interact with the HTML page, like click several elements, maybe the buy button, the HTML will call corresponding event handler in the JS file, which we call it the logic layer. And the logic layer will communicate with 2 parties. One is the workspace server to access the user resources, like the user ID or its Gmail and other things. The other is that the logic layer are also corresponding to interact with the add-on's own server, maybe query whether this user is a paid user or other things. And the random layer and logic layer, they together form the add-on source code. And this source code are actually stored in the Google Workspace rather than by the native add-on servers. And in the normal cases, not only the developer's permission, like the developer are able to develop and deploy the add-ons, I will also the add-on which possesses the secret key can use this to access its own third-party service or the database. Once this confidential information or the permission are leaked to the attacker, it can cause severe problems. We can see this is the normal cases. All of this, the permission and the secret should be protected by the cloud and never leaked to others. If these are the vulnerable and accessible to the attacker, the developer will lose their permission and also lose their confidential information and service. So this is our work, but there are 2 challenges in this study. First, as we all know, Google Workspace and its add-ons are emerging ecosystem. So how can we recover the unknown development protocol currently adopted by the developer? Second, even if we recover the protocol, as these are new, so how can we make sure that our analysis is comprehensive and we can identify all the security vulnerabilities existing in this protocol? In order to answer these challenges, we come up with our own solutions. So we will enumerate the add-ons as a developer. We registered to be a developer and do the reverse engineer. During this process, we will enumerate all the elements and record all the network and do the network analysis. After we have recovered the protocol used by the developer of the add-ons, we will test every entry point to see whether they are vulnerable or not. And then we can see whether we can access the code or we can access the permission. After we are able to access the code, we are able to successfully retrieve the source code. And based on this, we will do the hint analysis to recover the potential secret key along with their attack path and recover the exploit path used to access the database and retrieval, like this is the confidential user license in this case. And in the develop phase exploration, we register to be a developer. We enumerate all the interactive elements like the button, the code box, and the enumerate elements. We will interact with these elements and record the HTML page change and the network during this phase. This allow us to successfully retrieve the DevOps models, just similar to other application used. It was divided into two environments. One is the develop environment, the other is the production environment. And the add-ons are able to invite more collaborators, like distribute its develop and deploy permission to others. And this means that this permission may also be exploited by the attacker. Further, when the users interact with the add-ons in its own browser, the workspace needs to send the add-on code from its develop environment to the production environment, and in this process, the add-on code is also leakable. And during the operation, so we run the add-on for around 1 week and recorded all the network transfer during this phase. We configure that this domain name of the network can be classified into two types. One is the request sent to the workspace service. The other is sent to the add-on own server. And for the workspace server interface, actually it's a two-step. So the add-on will use its application ID and the user ID to exchange for the key provided by the workspace, which is the W key. And he can further utilize this W key to invoke the corresponding service, maybe fetch the Gmail attachment. This is protected by the Google Workspace and is secure enough. While on the other side, the add-on developer will communicate with the add-on service using its own key, which we call the A key, and this A key may be leakable to the attacker. And this is the overview of our attack. So when the user interact with the add-ons through their browser, the Google Workspace will transfer the add-on ID, and this ID can be captured by the attacker through the network traffic analysis, and then he can further encode and recover the corresponding link used for the develop and deployment permission, and also the link used to access the add-on code, and then we further verify whether the interface, like the project deployment interface or the add-on code, are available to us, rather than returning the 404 unauthorized access. If we are able to fetch the add-on source code, we can further do the hint analysis to recover the key used to access the add-on service using the hint analysis. And this is our evaluation. Around 300 add-ons with code leakage. We can see, although with the increasing of the user installation, the vulnerable add-ons, the proportion are decreasing. But for very popular add-on with 100,000 installation, there are still around 11 of them are vulnerable to the code leakage. And around 50 of them are vulnerable to leak their develop and deploy permission. In this case, the malicious attacker actually can not only develop in the developer environment, but also can deploy their modified vulnerable add-on and distribute it into the production environment. In this case, both the developer and the end user become the victims. and around 100 add-ons actually expose their secret keys. As we can see from these examples, there are many keys like the API key, AWS keys, and also the Stripe token. The Stripe token is actually used for accessing the financial service, and the add-on actually hard-coded its secret key, and we can use this to access the financial account of the add-on developers. And for our meditations, actually we provided 3 types of meditations. First, currently all developers assume that the workspace code is secure enough, but actually it can be manipulated by the attacker, and we encourage them to use the external tools like the AWS Security Manager or Google Security Manager rather than hard-coded their secret key. The other is use the authentication to verify every request sent from the attacker or sent from the normal user like the Authn 2.0 or the JWT, and also verify the original. We encourage the developer can attach their metadata, maybe the customer header or HMAC tokens when they send requests to their own server. This allows them to distinguish between the valid request from the workspace and also the malicious request from the attackers. And that's all my presentation. Thank you for listening, and I'm ready to answer your questions.